As mentioned in the last video, for examples 1 through 4, you can graphically determine the solution to a system of linear equations. However, unless the graph is originally scaled correctly, there might be instances where you're not going to be able to tell where the intersection point is actually occurring. This will particularly happen if you have fractions or decimals involved in solutions. And you won't necessarily know how to scale the graph to make it work until you know what the solution is. So that leads to a potential difficulty in how are you going to know how to scale it before you know what the solution is if you're going to be using the graph to determine what the solution actually is. So algebraically is the way to go most oftentimes to know where two lines are going to intersect and where the solution to a system of equations is going to be. And there were two methods that you learned in your high school algebra days about how to do that. And so this video is going to review those, and I'm going to give recommendations about when it's probably best to use one versus the other. Although you can use one solely or the other solely, it doesn't matter. As long as you have it set up in a way that it can be used, you're good. Now, one of the ways that you have of solving a system of equations are situations that particularly work well if you have at least one of the equations solved for one of the variables, like this one here. Now, if you don't, you can always solve one of the equations for one of the variables. And just to keep in mind that sometimes you'll see them presented like this. Your book likes to align the equal sign, so you might see it more along the lines of this. Doesn't matter. But as long as you have one equation solved for a variable, substitution is probably the more direct way of going. The goal when you're solving a system of equations is that you do want to get to a point where you have these two equations, each of which have two variables involved. You'd like to find a way of getting an equation with just one variable involved so you can solve it algebraically. So what can be done here is, since this one is solved for y, you know that y is the same thing as 3x minus 7. So you know what y is in terms of x. And therefore, if you use substitution, you can go to the second equation, the other equation, and put 3x minus 7 in the place of y. Now what you have is a single equation that has only one variable involved. And so if you carry this out by simplifying the left-hand side, so distributing, combining like terms, now you're going to isolate the x, so you would add 35 to both sides, divide both sides by 27, you get that x equals 2. Once you know what this value is, remember, you have to have both the x and the y for it to be the solution. You can go back to the first equation and then substitute this 2 in for the x. So y equals 3 times 2 minus 7, which is 6 minus 7, or negative 1. And oftentimes when you express a solution to a system of equations, you're going to give an ordered pair, because that's representing a coordinate, and it's going to be 2 comma negative 1. Most of the time, ordered pairs are always in alphabetical order, so if they're not x and y, you're usually going to put them in alphabetical order, and if you were graphing them, the first one is always going to be your independent variable, the second one's always your dependent variable. Other situations like this, although this second equation, it wouldn't take too many steps to isolate the y, although you could isolate the y up here, but you're going to be dealing with a lot of fractions. This one is set up more to do elimination. Elimination is also known as linear combination method in some other textbooks. But essentially, if you're using this method, what you want to eventually do is add these two equations together. And in the process of doing that, that should make one of the two variables cancel. In order to set that up to make that happen, you want to get the same number in front of a variable but opposite signs. And oftentimes you get to choose which one you want to do. I mean, you could choose to eliminate the x's, you could choose to eliminate the y's, and sometimes that choice will affect how much work you have to do to carry this through. Now in this case, in this example, I'm choosing to eliminate the y's. One, because there's a 1 in front of this one here, so it's not too difficult to figure out, well, what do I need to multiply this by to get a 7 in front? Well, 7. And you can see these already have opposite signs. So there's a little bit less to contend with, and I only have to change one variable. But I can't just change the one variable in the equation. I have to multiply both sides by 7 to get that minus 7y I want to have there, and keep the equation essentially equivalent. So the top is unchanged, the bottom becomes 28x minus 7y equals 56. Now, when I add these two equations together, the y's do cancel, they eliminate. That's the name, that's why it's called elimination. The linear combination is why, because you're adding two different equations together. I now have one equation that's 30x equals 96 that can be solved for x by dividing both sides by 30. And when you simplify 96 over 30, you get 16/5. Now you can go back to one of the two original equations, it really doesn't matter which, and you can substitute the 16/5 back in again. So I'm going to choose the top equation. Substituting 16/5 back in and carrying through the calculations. Now 2 times 16/5 is 32/5. Because I know I'm going to need to do a subtraction on both sides, I converted this into fifths as well to get a common denominator. So I subtract 32/5 from both sides. I'm going to divide both sides by 7, which is the same thing as multiplying by 1/7, and that gives me 24/5. So my ordered pair solution would be 16/5, 24/5. And so that is the end of this demonstration, which reviews the two algebraic methods of solving systems of equations. Please make sure to review special case solutions and then work on the remaining examples in this lesson.